Hello, hi everybody. Yeah, thanks for having me. I am going to apologize in advance because I think most of what I'm going to say is very kind of commonsensical, but hopefully will be useful for the discussion. I see a couple people I know in the background, which is nice. Um, so so yeah, I'm Adam. I have long time ago I did work on DNA nanotechnology in William Shee's lab. Was involved in the early development of the software called CAD Nano with Sean Douglas, who's a UCSF professor, was leading that. And Yeah, I've been thinking a lot, just basically very commonsensical thoughts, I think, about this idea of molecular 3D printing. Um, which is maybe a little bit distinct from some of the other ways that one might more directly try to go for like diamondoid type atomically precise manufacturing. So let me just share my screen. I'll try to introduce this concept of molecular 3D printing. Can you see my screen now?
Yep.
Okay, awesome. Um, right, so molecular 3D printing, molecular additive manufacturing. I'm not really trying to add anything new here. This is sort of me trying to translate for everybody a bunch of stuff that I think has been really talked about in this molecular manufacturing literature for a long time. Many people have talked about the idea that um, you could have building blocks, you could have sort of chemical bricks that you could bond together using like relatively standard room temperature, kind of if you want kind of bio-like reactions. Like um, there's this book called Bioconjugate Techniques, right, which is just a list of huge number of different reactions that you can sort of do in a aqueous, salty, roughly room temperature test tube that people use a lot for different types of biochemical reactions, right? If you have an antibody, you want to link some chemical, a piece of DNA to it or something, you'll use one of the reactions in bioconjugate techniques. Um, and the question here basically is like, well, can you use those like standard reactions, relatively standard building blocks, and can you combine that with some kind of positional control so that you can positionally specify, which brick or building block gets bonded to which, um, but you're not actually trying to go to sort of angstrom scale manipulation of these like atomic orbitals, right, to get particular reactions to happen. You're just like pressing go on reactions in the bioconjugate techniques book, but you're doing it essentially in a way where the things that are available to react with each other because of local concentration differences, because you move something just sufficiently near, it's just going to with high probability react to one that's nearby versus other equivalent sites. So that's essentially the intuition behind this. Um, so and I think this still counts in some way as a kind of prototype of a positional controlled molecular manufacturing type system, because it would be able to create individually specified chemical bonds at scale. It would just only be doing that between a restricted set of bricks, right? So there'll be otherwise equivalent bonds that you could form between different subsets of the bricks that you're not forming, and you're not forming them because you're actually specifying positionally with the placement. Um, and like in many ways, you can see just the ribosome as a kind of example of something like this, right? So in that case, the building blocks are these amino acids, or you could say that there's these like charged tRNAs that are carrying the amino acids. Um, and essentially what the mRNA of, coming into the ribosome is doing, it is determining which one is going to be in and available inside the ribosome and able to form a linear, next bond on the peptide chain. And it's not taking any arbitrary atoms within those building blocks. It's just taking the N terminus or the C terminus of that amino acid and adding it on. So they were talking about bonds between finite sized building blocks, but we can control in a programmable way which bonds, when we have otherwise chemically equivalent bonds, you're controlling which ones are actually going to form versus not. So you could say this is making a 1D chain. This is a kind of like a 1D chain version of what we're talking about. And the question is just, well, could you engineer something that would do a 2D array of these building blocks that also specifies the kind of the XY, which of several building blocks locates itself in XY, again with covalent bonds. So you might have, instead of a building block that has an N terminus and a C terminus, to basically link to the end of a peptide chain, you might have, let's say, squares that have 4 corners, right? And each one of those, can be linked to its neighbors. Or in the 3D case, you would have some 3D version. So could we make something like the ribosome that can assemble 2D or 3D chemically linked structures? And then, can you do that not just under the control of the sequence of that mRNA, but can you do that under some kind of external driving or external control? And, positional control is like a way that you could do that. So in this workshop, we discussed several different versions of sort of concepts for systems that could do something like that. I'll just go over, each of those. But the molecular printer, I think, is kind of the essential one, maybe to focus on. And so there are 2 different versions of this. This is borrowed directly from Eric Drexler, maybe unsurprisingly. So one version of this, you have some set of building blocks already in place, and all that you're doing is, with your positional control, is you're controlling which of these blocks have some deprotection, right? So they become activated to be able to react with other blocks when they're already in the structure, and you're controlling which ones get activated with this positional tip. And then the actual adding on of the second block, you don't have any positional control. Those blocks just go in and they diffuse in the solution, but they're only going to be able to react with the activated sites. Okay, so the positional control is using for activation, or it's using for deprotection of certain sites. And then you can do that, and then you repeat a next cycle where you activate another subset, you flow in another family of bricks, and let's say the green bricks will all add to the appropriate activated sites and not to any of the sites that weren't activated. So that's one version where you don't even need to bring the thing you're reacting to with or adding on. You don't need to bring the brick directly to its partner. You just activate or deprotect. And like, I think the intuition behind this, or the concept behind this, is like these bricks now would be something that are like medium size, like organic chemicals, right? They might be a couple nanometers in size, like pretty large size organic chemicals. You sort of think of like something around the size of amino acid, maybe a little bit bigger, or this amino acid tRNA. So you don't have to specify, as long as you basically have positional resolution of which one is getting deprotected or activated within a couple nanometers, essentially, you're still able to specify which block, which sites are going to have a given type of block get added here, right? So that's one concept. The other concept, and this is a figure from some of the work that was funded by David Forrest, DOE program on spiroligomers. So spiroligomers are maybe one family of like brick that you could use in this category. You can make these spiroligomer molecules that might be have different functional groups, let's say on 4 corners of a square, if you're thinking about the 2D case, and that are a couple nanometers in size. So you have like a reasonable level of positional control. And 2 nanometers, right? That's small, but if you think about like, even the spacing of 2 adjacent, sites on DNA, right? That is actually like a fraction of a nanometer between one nucleotide and the next along the chain. The DNA origami kind of positional resolution of what you can make with DNA origami, potentially the types of motors that you could make with DNA origami or protein engineering, they could be maybe in this range. It's maybe a stretch, but there doesn't seem to be any reason why you couldn't do it in this range. And so this is from the 2007 Foresight-Battelle roadmap, where Schaffmeister was proposing a sort of different scheme, where in this case you are directly bringing in the spiroligomer brick that you want to bind to the next one and react. You're actually bringing it directly, right? So it's not just this activation deprotection, you're bringing it and then you're releasing it after it reacts. So that's a slightly different version of the molecular 3D printer with these couple nanometer sized bricks. So he has like this whole specification in the 2007 paper about like how would you make this. It's an early concept, but it's like the kind of thing where it doesn't seem obvious that there's like any reason you couldn't do something roughly like that. And then there has been some progress, right? So it's early progress, but this is a DNA origami machine essentially that is trying to do make essentially the thing that would do the programmable positioning. So I think this thing is not quite at the level where it can just directly go with, sub 2 nanometer resolution and just reposition in real time, but it's a step in this direction where they can get this 2D arrangement to reconfigure. So this was another one from their DOE proposal of what they're thinking about trying to do. They were planning to sort of have more like 3.5 nanometer resolution in this project. Initially, they would just be placing different little pieces of DNA at different locations on this breadboard. But it's like another step from that. You would have sub 2 nanometer. Maybe you'd be using spiroligomer bricks, or you would have an activation or deprotection chemistry that could unlock certain sites so that they could then react, and then you could do it again. So there's some sort of preliminary progress along this general direction. I think it's really interesting that like basically it seems like you don't get much progress along this direction unless someone has a funding call, right? So when the DOE actually had a funding call that said we want this, then these labs basically responded and they made this thing. And it seems like when they don't have a funding call out that says I want this, this labs sort of don't go after it. So it's just interesting. This is also from William Shih, where it's a slightly different version, where they're not trying to like have a motor that moves these positioning. They're just trying to make a template that pre-positions all the bricks. And then at a certain point, you just say go, and they will react with their neighbor. So it's a spatial scaffold to pre-position the bricks. So they're proposing to do that on top of a DNA origami. That's another way you could start prototyping. It doesn't have to have dynamic motion. You just show this idea that by positionally restricting which brick is next to which, and then using, again, these, like, let's say, relatively standard reactions from the bioconjugate techniques book or similar, if the size scale of the bricks was matched to having the kind of level of spatial restriction that you can have with the DNA origami, you could just, one shot, basically template this on a DNA origami, have these local reactions that kind of crystallize this all together, and that would be a kind of one-shot form of a printer. Maybe less rapidly programmable, but in principle, you could program this by the DNA origami. So those are kind of the main, I think, concepts. There's some sort of ancillary versions where, what if you don't need the printer at all? What if you can just sort of use spiriligomers and the order in which you add things and the order in which you deprotect to make something. And then there is the sort of separately, there's more like the STM AFM directly manipulating forming particular chemical bonds at a kind of higher resolution. Yeah, that's basically the summary of a few different architectures. And so they have very different characteristics, but I think it was just interesting is like, you seem like the interesting thing to me is like, not even how far can you go with this? It's like, can we get research progress on this at all, right? And so like when the DOE makes this funding call for like something that looks a little bit like this, you actually see this little spurt of research progress, and that you see some of these things come out. And when they don't have that funding call, it's kind of you don't see it. So it sort of seems like there's this overhang, and it's like, could we test out these different types of systems? I think there's a long path right from there. There's no claim that I made in that the things you would print would in turn be better, be able to print something even better, right? Maybe that's possible. But there's just this basic question of can you use this as a way to link bricks together covalently? Yeah, so that's kind of where we are.
Great. Thank you, Adam. We're all clapping here.
Sorry to be remote, and hope you enjoy the rest of your
workshop. We actually have a few questions, if you don't mind.
For sure.
Does anyone have one? Otherwise, I'll kick us off with one. So, for example, Juan would love to know what's the kind of like number one thing holding back progress right now, and who do you think is doing interesting work in this field right now? Like if we were to kickstart like a larger effort in this, who would you be pointing to, and like what's really bottlenecking progress here, according to you?
I mean, on a sort of separate line from what I just discussed about the solution phase reactions and everything, I am very interested in what the Canadian company, what type of progress they've been able to make in sort of where that gets us on more scanning probe based methods. But in terms of this, I think that it's a difficult area to bootstrap, right? Like if you imagine I'm sitting down, I'm a graduate student, I'm even in the right lab. I'm in a lab that does DNA origami, and I have a chemistry background. So in principle, I could try to work on this slide that I show where you use DNA origami to template these brick reactions, right, with spatial control. In principle, I could do that, right? But like, is that a great thesis project, right? Because what's, if I'm doing a biology degree, what's the biological relevance of that? Can I directly make a drug? Not really. If I wanted to say, hey, I want to make this particular chemical, right, it's going to be somewhat unreliable at first, right? It's not clear exactly what the application is for those first generations of thing, right? So we're sort of talking about a basic engineering, if you will, right? Basic science. This is sort of basic engineering. Can I do it? What are the principles for doing it? What bricks would I use? How good can I make it? And it's getting that into a cycle where the thing you make next is actually better than what you could have made by some other method, right? For any given application is hard. And so you kind of need this like DARPA-like approach where they fund you only conditional on you hitting certain milestones. And you basically organize this idea of a coordinated research program, right? Of how do you pull the researchers to integrate pieces in a way that they might not naturally feel incentivized to pull in order to do those demonstrations, which could then show, okay, yeah, this idea of positional control is not totally crazy. We could do it in practice. And then maybe that next round, the next round might be a DARPA-like program that would have real applied goals, right? But the first one would first phase would just have to have a demonstration.
And what do you think that may cost? Like, yeah, what do you think that may cost from a funding perspective? And like, are there any kind of applications that we can point to at the end of the road, that funding could enable?
I mean, the way I like to think about these things is like, let's say you need, 2 scanning probe experts, 3 biologists, 2 chemists, 2 project managers, a CEO, and 3 research assistants, right? So you talk about, okay, well, you 12 or 15 people all working on the same project. And let's say you need to iterate several cycles on this. You also need reagents, whatever. So you want to do that for 4 or 5 years, right? Just in a concerted fashion on a single project, not each one thinking, oh, hey, here's this most interesting biology paper I can do, or here's this most interesting applied startup I can do. It's like, we're just going to work 12, 15 people on this thing focused. And so you say, okay, 15 people times their salaries, reagents, lab space rent, or whatever. I think you talk about, low tens of millions of dollars, right? If you talk about 5-year projects, a couple dozen people, right?
And that gets you what, you think?
That gets you, in my opinion, it gets you just these really like proof of principle demonstrations, like the thing I talked about on this slide, except it's like experiments. It does not, in my opinion, get you directly to a real world useful application. It's not clear that that first round of work actually gets you to a kind of bootstrapping where the thing that you made is now better to make the next version than just making the next version from scratch, right? But it gets you that demonstration, which could then engage more researchers and bring more talent effectively into working on it. So, and maybe I'm a little pessimistic, but I think you need to spend a couple tens of millions of dollars just to do demonstrations of what I talked about in this slide of the most basic character, and probably would be similar with the scanning probe type things, just to demonstrate that you can make interesting, 3-dimensional structures, maybe simple machines with positional control, without actually requiring that you meet an applied kind of end user goal there.
Awesome.
Other than showing it. Yeah.
Thank you. We hear a little bit more about Jeremy's work as well later on the STM side, so that'd be interesting.
Yeah, I'll be curious about
Okay. Any other questions, comments? No. Thank you so much for joining.